Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at a set of conservative forces and introducing a new concept called potential energy, and that's going to allow us to look at the concept of conservation of total mechanical energy as a way of solving mechanics problems. Now, we've already introduced the idea of the work energy theorem. This is the connection between kinetic energy, the change in kinetic energy, which is a measure of the energy of motion, and tying that to the forces acting on an object, and specifically the forces acting along the direction of motion or against the direction of motion. And so that gives rise to our expression for work, which is the integral of force dot displacement, or the element of displacement along our path. Or if that force is constant, it's just the force dot the total displacement. But that dot is important because it tells us that it's only the forces that are acting along or exactly against the path of motion, the displacement of motion, that actually play a role in changing the kinetic energy of an object. This is the equivalent of Newton's second law, F equals ma, but it's written in a way that we're using scalar quantities, and it's particularly useful for forces that have a position dependence. And we actually have already seen several forces that have position dependence, such as the spring force and the gravitational force. So this will be a way of actually approaching problems using that force law where we don't have to worry explicitly about time. Now, we've also introduced the steps for solving these kind of energy problems, and it's very much similar to the way that we solve our Newtonian problems. We set up our knowns and what we want to solve. We make some predictions about the motion. We set up our force diagrams, and we figure out which way the forces are pointing along inertial coordinate systems. And from that point, then we can calculate our kinetic energies at the initial and final positions of time that we're interested in terms of this problem. And we can calculate the change of those kinetic energies using our work energy theorem, and from that we can actually solve for any of our unknowns using our expressions for kinetic energy and work. Now it will involve solving this integral or calculating the work itself, but we'll see there's actually some cases where that integral is very easy to do because it doesn't actually depend on the path that the object follows. Now, to illustrate this, let's just take a simple two-dimensional space and consider 2 points along the space, an initial point and a final point, and assume that we have a force that's acting in the negative y direction in this particular space. So if I follow one particular path from our initial to final point, I can calculate the work that's being done on the object as it travels this path by just adding up all of the force dot displacement elements as we travel along that path. So that's what this integral actually calculates. Now, because this is a constant force, all we're really doing is just adding up all of the y components of our displacements and multiplying it by negative f because it's pointing in the opposite direction. And so when you add all those up, it's just equal to the force times the total y displacement. And because we're increasing our y coordinate, this is going to be a negative sign, so that we're actually doing work to slow down the object. We're doing negative work on the object. Now, if we look at a second path from the same exact points, and it could be a very convoluted path, when we do these little integrals along each of these path steps, we're still calculating essentially the same number, the displacement in the y direction times the force, and if it's a positive displacement in y, it's going to be a negative work. So adding up all these little paths is going to give us exactly the same quantity at the end. So even though we followed two completely different directions or trajectories to get from our initial to final positions, the work done on the object is exactly the same because it depends on a constant force and just the displacement between the initial and final positions. In fact, this is an interesting observation. The work done depends only on the initial and final points. It doesn't depend at all on that path in between. This kind of behavior, where the work just depends on the endpoints, is something that we can take advantage of to solve our work energy theorem in a much faster way. So we have a whole class of forces that we call conservative forces, and those forces satisfy this property that the work done, or the change in kinetic energy, only depends on the endpoints and not the specific path that the object follows. And this is called a conservative force because you can imagine if you start at a point A and travel to point B and you have some change in kinetic energy, by going back to point A, by any path you want, you're going to end up with exactly the same kinetic energy because at that point the endpoints are at the same point, so you haven't moved at all, and in the end you haven't changed your kinetic energy. So even though you may slow down or speed up as you go between point A and B, you get that kinetic energy back when you go back to the original point. So somehow this energy is stored somewhere, or conserved somewhere, somewhere in the force law, and we always get it back by going back to the original point. So that's why these are called conservative forces. Now, with that idea that we can store the energy that we're gaining or losing in our motion in this conservative force, we have this new concept called potential energy. And this is the energy that is somehow stored in our conservative force that has the potential to change our kinetic energy, either in a positive or negative sense. And this is really just back to our concept of work, where we're going to compute the potential energy, or at least the change in potential energy, as the negative of the work done by the conservative force, or minus times the integral of force of conservative forces dot the displacement along the path. Now, the interesting thing is, of course, that because the displacement along the path is independent of the path, it's very easy often to calculate these potential energies. And when we add kinetic energy to potential energy, that sum is another new quantity that we'll call the total mechanical energy. So just to keep track, we've got kinetic energy, which is the energy of motion. We've got potential energy, which is the energy that's stored in this conservative force. And we have the total mechanical energy, which is just the sum of these two. We'll see why this is important in just a moment. But first, it's important to look at what are some of the potential energies that we might see in our sort of force laws. Again, to calculate this is just doing the negative the integral of the force dot displacement. And often, again, because the force doesn't depend, this integral doesn't depend on the path itself, it's often easy to actually calculate this number straightforwardly. So a great example is the kinetic potential energy that's caused by gravitational acceleration. If I start from some height h and I'm going down to a ground that we'll call 0, we're obviously gaining kinetic energy, we're speeding up. Where does that come from? Well, it comes from the potential energy that we started off with at height h. And if you do the integral of the force, which is m times g, times the height, the negative of that gives us mg times h. And that's potential energy of the gravitational acceleration here on Earth. We have similar expressions for the gravitational energy for a spring, which is 1/2 k times the displacement of the string from its equilibrium state squared. And we have an expression for Newtonian gravity as well, where you get a negative sign because you actually have a negative potential energy when you're close to an object. It takes kinetic energy to get away from the object, and it depends on 1 over the distance. So all of these expressions can be solved for by just simply solving our integral, but it's a general expression for the potential energies, and we can have different potential energies for different forces as long as they satisfy this criteria, where the force, the work done, doesn't depend on the path, but it just depends on the endpoints. So when we talked about the kinetic energy, we knew that it was 1/2 mv squared, mass is greater than or equal to 0, speed is greater than or equal to 0, so kinetic energy can only be 0 if there's absolutely no motion. Potential energy, on the other hand, we're only measuring the change in potential energy when we're moving from one point to another one. And so you can actually have an arbitrary 0 point for both potential energy and, by extension, the total mechanical energy. This is exactly the same as just defining our origin no matter where we want it. If the potential energy depends on position, of course it's going to depend on where we set our 0 point for our coordinate system, and that's an arbitrary choice. So you'll often see cases where the potential energy may be positive or negative, and that's okay. It all really depends on what the change of potential energy is. So using as an example our potential energy from just raising something up in our surface gravity, if we start from, if we set the ground, for example, as our 0 point, then we can calculate the potential energy as just mg times the height above the ground. But we can equally specify what the potential energy is relative to the top of the tree. And if we're moving down below the tree, then we've actually decreased the height, and we've actually lost potential energy. You can imagine that we've increased our speed as we fall down, and that means that our potential energy is mg times the height of the tree minus the height at which we end up, and that's a negative number. So don't worry about positive or negative in terms of potential energy. Just be consistent with setting the exact 0 point for potential energies. As long as you set that, then all we really care about at that point is just the change in potential energy and not the absolute value. Now, we've talked about how the sum of kinetic energy and potential energy is this total mechanical energy. And in the case where we only have conservative forces, it turns out that that total mechanical energy is always conserved. And we can just see this from the way that we've written our kinetic energy, work energy theorem. If the work done is only done by conservative forces, then the change in kinetic energy is just equal to minus the change in potential energy. And if I move that over to the same side, the change in this sum of kinetic energy plus potential energy, which is the change in the total mechanical energy, is going to be 0. So that means that no matter what path an object follows and what kind of conservative forces are acting, there could be many forces acting at the same time, in the end, the total amount of mechanical energy, kinetic plus potential, is going to be the same throughout the problem. This makes solving many complicated problems very easy because we don't worry about the details of how an object moves through its system. All we care about is the initial and final states of the kinetic and potential energies. So let's look at an example of this for the case of ballistic motion, motion that we've already solved for in our kinematic quantities. But let's see how we can solve this from the perspective of conservation of total mechanical energy. So let's take the case of just a basketball being shot by a basketball player. I can choose a coordinate system here where I've centered my coordinate system just on the point where the ball is leaving the basketball player's hands. So I'm going to set my 0 point for my y-axis to be 0. And this is also going to be the 0 point for my potential energy that's arising from the surface gravity force. So I can write down the potential energy then as it moves away from this origin. That's just the force of gravity, mg, which normally points down, and our displacement y, which points in the opposite direction. But it's the negative of that, so that flips that around, and we get a mg times the displacement in the y direction. So at the point where she releases the ball, you've got 0 potential energy, and then at the height where the ball is at its maximum height, you have some positive potential energy because you are some positive height above the point of the chute. And of course we can write down the kinetic energy at any one of these points as just 1/2 m times the speed squared. And because it's speed squared, we can break this down into the components of speed, both the x speed and the y speed. It's going to be vx squared plus vy squared is the total velocity squared. That's just from Pythagorean's theorem. So that gives us a kinetic energy at any one point. So now let's take a couple of specific points. Let's look at the initial point of where she releases the ball. We can compute the kinetic energy, the total mechanical energy at that point as the sum of potential and kinetic. The potential is 0 because we're at our 0 point of our y scale. And the kinetic energy is just the sum of the x and y initial velocities. So we just 1/2 m vx squared plus vy squared. Let's take our final point to be the top of the motion. And at that point we have an mg times our height term for our potential energy, plus we have the component of kinetic energy that's left over, which is just along the x direction. Remember, the top of our ballistic motion, the y component of velocity has gone to 0. But the x component of velocity never changes because we don't have any forces acting along that direction. So the total mechanical energy at that maximum height is just the 1/2 m vx squared plus our potential term mg times the displacement in the y direction. Now, if it's true that the initial and final energies are the same, then I can equate these two expressions to each other. And after doing a little manipulation, canceling out the m's, multiplying both sides by 2, we end up with this expression, which relates the initial speed, vy squared, to the gravitational acceleration and the maximum displacement. And of course, you'll remember that this is one of our original kinematic relations that relates the change in the speed squared to the acceleration and the displacement. And of course, that comes from energy conservation. So you can see how we're balancing back and forth between our original kinematic quantities and this new idea of conservation of energy. They're all tied together because ultimately they're all coming from Newton's second law that the mass times acceleration of an object is equal to the net force acting on the object. So this gives rise to a new problem-solving process, which is similar to the other ones we've had before, but this is the case where we're solving a conservative energy problem, where all the forces are conservative, and we can just consider the endpoints of the kinetic and potential energies. Now, as before, we follow similar sort of steps in sort of setting up the problem. We want to write down our knowns and figure out what it is we're solving for, make some predictions about what we're solving for, and then break up our problem into its key interacting parts, and draw a force diagram for each of those parts to know which forces are acting. But at this point, we depart from our original solution problem because we don't have to compute the work in this case, because the work is entirely contained within the potential energy. So all we have to do is consider our initial and final points and calculate the kinetic and potential energies at both of those points. And then we equate those to the total mechanical energy. And if there's only conservative forces acting, that number, total mechanical energy, is going to be constant. So we can use this conservation of total mechanical energy to solve for our unknowns, and that's the way we can get to our whatever quantities we're actually searching for. Now again, this is a procedure that works only in the case where we have all conservative forces acting. We're going to see in a little bit how we can fold into this other forces that may not be conserving energy, or so-called dissipative forces. So to summarize, conservative forces are a class of forces that perform the same amount of work on an object independent of the path. These include many of the forces that we've looked at, such as the spring force, the gravitational acceleration force, Newton's law of gravity, constant forces. All of these fall into the category of conserved forces. And for these forces, we can define a new energy term called the potential energy. And at some level, this is the energy that is stored in the conservative force and can be put back into kinetic energy as an object moves around the force field. So that's just equal to our expression for the work term, but it's the negative of that because this is the work that's going to be done later on in the object when it moves in a different part of this potential field. Now when we add up our kinetic and our potential energy, that together is the total mechanical energy. And in the absence of any non-conservative forces, that number is going to be conserved for our system. So no matter how complicated the motion is, we can still count on that number, the total mechanical energy, being the same throughout. So this is a very powerful technique for solving sometimes complex physics problems. So take a look at your examples and make sure you take try to experiment with measuring kinetic and potential energy and using this conservation of energy for solving these problems.